All right, problem number 17, a little baseball problem here. We have the center field fence at a baseball field is 10 feet high and a distance of 400 feet from home plate. Player hits the baseball when it is 3 feet above the ground. Let theta equal the angle that the baseball leaves the bat, and let the baseball be hit with a speed of 145 feet per second. And we're going to assume negligible wind resistance because we're going to keep these calculations a little more simple. They're involved enough. So first thing we want to do is label a right triangle vector diagram to figure out what is the vertical and the horizontal component of that velocity, the speed with which we're hitting the ball. So think back to what you know about vectors. Remember, vector is kind of like a little right triangle, where the magnitude is on the hypotenuse, the magnitude being the speed, 145. The angle there is theta. We don't know what it is right now. We're going to try some different theta values and see what happens. But we can now write the vertical component of this vector using some trig. We know that that vertical piece is going to be 145 times the sine of theta, and the horizontal piece is going to be 145 times the cosine of theta. So there you have that. Next thing we want to do is write the parametric equations x of t and y of t that model both the horizontal and vertical location of the baseball at any given time t. So let's do x first. Think about what's happening here with our x distance. Our x distance, we're talking about this outward distance. We're not talking about up and down. We're talking about how far away from that home plate is it, assuming it follows out in that linear manner, which it should, going straight out towards center field like that. We want to know what is that x value at different spots. Well, think about what we're doing. We're taking that baseball and we're launching it away from this batter. So I'll give you a little hint here. Remember that rate times time will give you your distance. And so we're talking about a distance away from that batter, distance x. Well, what is our rate? Our rate is the horizontal component of that velocity. So 145 times the cosine of whatever that theta works out to be. That is our rate, and all we need to do is multiply that by our time. Alrighty there. Well, what about y? For y, we are talking about now the vertical aspect of the ball here. How high is that ball at a given time? What is the height, the y value of that ball? Well, here we need to remember our vertical motion model, which we should remember is quadratic. It's going to be negative something t squared. What is that something? Well, it depends on the units. Our units are feet, which means our coefficient needs to be negative 16. And then we have t squared plus our initial velocity, but we need to make sure we are using the vertical component of our initial velocity, 145 times sine of theta. So 145 sine theta, it's going to be this piece times t. So remember, negative 16t squared plus v naught t plus h naught, and what is our starting height? Our starting height is 3. And so now we have two equations here, an x and a y, forming our parametric equation set, which models the position x and y of this baseball. So now it says graph the equation and determine if it will be a home run if the ball is hit at an angle of 15 degrees. So a couple of warnings: make sure your calculator is in parametric mode. It'll either say PAR or it'll actually spell out parametric depending on your calculator model. And also make sure you're in degree mode since we're using trig functions. And we're going to write these angles in terms of degrees because we're hitting it at an angle of 15 degrees. So let's think about what this equation is going to be. Well, the equations are going to be exactly the same as what we have up above, except instead of theta, we're actually going to put in the theta value that we are hitting the baseball with, which in this case is 15 degrees. So I'm going to get rid of both of those thetas and put my 15 in there. Maybe throw some parentheses right there to make it look a little better. Okay, so let's graph this equation. So we want to enter those equations in parametric mode. Don't forget to close the parenthesis after your trig function. And we're going to need to adjust our window if we want this to work out well. So hit the window button. T min, let's do 0 because that's going to represent 0 seconds. T max, let's make a reasonable guess. If you're hitting a baseball and we're trying to hit a home run over a fence that's 400 feet away, what would be a reasonable number of seconds for that to be in the air? Well, honestly, I don't know, but probably what, like 10 seconds? Maybe a little bit more, maybe a little less. I don't know. Let's try 10, maybe let's try 15 just to be safe. All it's going to do is graph a little bit more of the parabola if we increase that T max. T step, again, is going to tell you how often it's going to plot those points and connect the lines. So do a small value. Since our maximum T value is only 15, let's do something small like 0.1. That will then graph a point every tenth of a second, which is kind of cool. X min, well, remember X is representing our distance from the batter horizontally. So let's put that at 0, representing home plate. X max, let's make that the fence, 400 feet away. X scale, make it whatever you want. I'm going to make mine 50, so it'll put a tick mark every 50 feet. Y min, I'm going to go a little bit below the ground, so I'm going to go -5 for that. Just, for fun for some reason. I don't know. Whatever. Y max, what should we do for that? Well, we want to be able to see the top of this baseball. I don't know how high it's going to go, but it's probably not going to go that high. Again, I don't really know enough about sports to say. What do we try, like 60 feet? Who knows? I don't know. Scale, again, I'm going to go 10 on that one, so it'll give me a tick mark every 10. And let's graph that and see what happens. Hey, that actually looks pretty gosh darn good. Maybe looks like we have way too much time. If you can see, that graph is still going if you look in the upper right-hand corner. But we have a parabola, and we can see everything, which is sweet. So if you enter the function as I did, and you use the window settings as I did, you should end up with something that looks like this. But how do we now use a calculator to determine if this was actually a home run or not? Well, think about what a home run means. Home run means that when the X value is 400, the Y value is something that is greater than 10, because we need to be above that 10-foot high fence. We want our baseball up there. That's what a baseball looks like. So how are we going to determine if that is the case? Well, you could trace it. Hit trace. You can move your cursor along the graph. Oh, wow, look at these t-values. Apparently baseballs move a lot quicker than I realized already. And let's see what happens. Let's trace over to about 2.5 seconds. Notice our X value is 336 and our Y value is already down to 0.9. Which is telling me that, nah son, we did not hit a home run. So there is no home run right there. With an angle of 15 degrees, you will not hit a home run. That's good to know. And it'll land roughly 337 feet away, and it'll take about 2.5 seconds to get there. If you go exactly 2.5, you'll see that it's already hit the ground. It's about 350 feet away. What about 2.5? I don't know. We can go even closer. 2.4. We already did that. 2.43? 2.43 is just after it hit. I know it's just hit because the Y value is -0.28, which means it's just hit. Our graph doesn't know that the ground exists and the parabola is going to stop and it would bounce back up. But there you have it. I don't know. Okay, now what can we do from here? Well, let's look at D. It says find the smallest possible theta that will result in a home run. The shortest home run is the point 400, 10, right? Because that would be hitting right at the very top of the fence. Maybe you want to argue about whether it would go over or not, but let's go ahead and use that as our benchmark for this. Well, now we basically just want to go in and modify our angles, that 15-degree angle, try something different and see if we can get close to this point 400, 10. So let's just try a couple different angles and see what happens. 15-degree angle didn't get me far enough, so maybe let's try a slightly larger angle. Let's see what happens if we try 20 degrees. So again, go in, change the value of cosine in both equations. I'm sorry, change the angle in both equations, so cosine in x, sine in y. And what I'm going to do is I'm going to try 20 degrees this time and see what happens. And if you do 20 degrees, you're going to end up with a very similar graph, except it's going to look more like this. Instead of seeing it go negative, it's going to end above the axis like this. Remember, the highest x value we graphed was 400. Whoops. So the last thing you see on this screen is actually the x value of the fence, that 400. That was kind of clever of us. So let's do a similar thing with our y-axis here. Let's go back to our window, and I think this is probably the easiest way to do this. Let's make our minimum y value 10, the height of the fence. That way, if we can see our parabola ending above that, we should know that we hit a home run. And if we can't, then we know that we didn't hit a home run. So changing that and graphing it, you get something that kind of looks like this when you graph it. Weird dots at the bottom. That's indicating that you do not have the x-axis there. But when we do this, we get a graph that looks much like that, which is actually showing us that it looks like we are hitting a home run. Now we can trace this graph and become a little more convinced that we hit a home run or not. So I'm tracing it, I'm increasing my t values, and I want to figure out what is a t-value that gets me pretty close to 10. Well, 2.9 for t puts me at a y value of 12, an x value of 395. That's not quite a home run. What about 3? Well, 3, now I'm below the fence and above 400, so let's try 2.95. 2.595 puts me pretty much right at 10 feet for my y value, and if you look at your x value, you're right at 401.95352. So x distance of 401, which is farther than the fence, y distance of just over 10. Homies, we just hit a home run by hitting this ball with a 20-degree angle. Now maybe you could go smaller and find like 19.9 and say, hey, that also hits a home run. Good for you. Go ahead and find the smallest one you can. For the sake of this video, I'm going to say you could play with it and find a closer one forever and ever and ever. But I'm going to go with 20 degrees is a pretty gosh darn good answer for this question.